Hello, everyone, and welcome to another wonderful day of PChem. So, today we're going to be talking about one of our old familiar friends, integration. So, throughout this entire semester, we've run into a lot of integrals. And in fact, by the time we reach molecular orbital theory, we ran into problems that probably will include solving hundreds of integrals. So, one of the reasons why integrals are so annoying when we run into them is this idea that there isn't always a simple solution to most of these integrals. And especially by the time we reach multi electronic systems, where our Hamiltonian changed to such a fashion that, well, our integrals got really messy. So, one of the classic questions is how can I try and help simplify a lot of these integrals? Well, one of the old strategies is using this idea of symmetry. So the major purpose of symmetry when dealing with integrals is the idea that it can help us identify when integrals go to zero. So if I'm dealing with a molecular orbital system and it turns out that 3/4 of my integrals go to zero, if I can figure out which ones those are, it's going to save me a whole bunch of time. And this idea of using symmetry to solve integrals is based on a fairly old idea you probably encountered in calculus. So this is the idea that if I try and integrate a completely symmetric form or maybe an asymmetric equation, that I'm going to, when I integrate this region, I will have a real value. I'll get some positive value when I integrate over this whole area. However, if I run into an anti-symmetric equation, a system that has equal positive and negative elements, it turns out that when I integrate this system, my value goes to zero. And this is really what I'm going to be looking for, is integrals that are going to be anti-symmetric. And one of the ways that this is going to apply to a lot of our point groups and our irreducible representations that we built up the last couple of lectures is that it turns out that our completely symmetric irreducible representation will give, if I integrate that, I will get a real value. But it turns out that every other irreducible representation is anti-symmetric. So if I try and take the integral of any function, specifically wave functions that's described using this using an anti-symmetric irreducible representation, I'm going to get a integral of zero. So what we're going to be looking for is when my integral will land in this category or this category. And this actually ends up becoming really helpful because a lot of our integrals are going to be based on the products of two different wave functions or two different functions in general. And so it turns out that if I try and take two wave functions, multiply them together, I'll only get a real value if if their product is the symmetric wave function or belongs to the symmetric irreducible representation. And it turns out that I'm only going to get the symmetric irreducible representation if my two original functions share the same symmetry. So this can actually be completed by analogy by going back to our original symmetry operations for C2V, which did a very similar thing. So if I first started with one symmetry operation and then applied a second symmetry operation, it turns out the only way I got to the identity I got the identity back is if I applied one one operation to itself. And it turns out that this actually happened, this exact same thing happens when I'm looking at irreducible representations. So this is the major idea that we're going to be looking for, is that if I take the product of any two irreducible representations, if they share the same point, if they belong to any two wave functions, if they belong to the same irreducible representation, I'm going to get the identity or the completely symmetric irreducible representation back. But if they belong to two different irreducible representations, I'm going to get some third irreducible representation back, and it will be anti-symmetric. So the integral of any product will be a real value if my two starting functions share an irreducible representation, and it will be 0 otherwise. So let's go ahead and work through some examples of what this means. So let's go ahead and start by working a system that's somewhat familiar. So let's take a look at our SO2, which belongs to the C2V point group. And specifically, we're going to be looking at the interactions in between the px and the py orbitals. So in order to do this, it turns out that the interaction can help describe the overlap matrix. So this will be the integral of our px and our py wave functions integrated over all space. And it turns out that this is going to be proportional in some meaningful way to taking the integral of the two respective irreducible representations. So by grabbing your character table, which I highly encourage you to do as we solve a couple of these examples, what we can find is that the px orbital belongs to the B1 irreducible representation, and the py orbital belongs to the B2 irreducible representation. So what I'm going to want to do is take the product of the B1 and the B2 irreducible representation and determine what that irreducible representation is. And you can take the products of these irreducible representations simply by taking the products of each of the individual values. So for the identity, everybody's 1. So the product of almost any irreducible representation, set of irreducible representations, will be 1. Now, in the second case, since they're both members of the B reps, they both have values of -1, which will cancel out, and the product irreducible representation has a value of 1. My sigma v, or xz plane, will have different values for both of our irreducible representations. So as a consequence, my product has a value of -1, and we can do the same thing for the other mirror plane, which will also give a value of -1. So if you go ahead and grab your character table, you will find that this point group is going to be this irreducible representation is A2. So congratulations. If I multiply these two together, I get the A2 irreducible representation, which, as you may notice here, is going to be anti-symmetric. It has equal numbers of positive and negative elements. So if I try and integrate the product of these two species, it's going to give me a value of 0. And this should hopefully make a lot of sense, because I just took the integral of the product of two wave functions of atomic orbital wave functions on the same atom. Congratulations, these two form an orthonormal set. And since they aren't identical, congratulations, these should be orthogonal wave functions. And that's exactly what we proved here. Symmetry helps support the argument of two wave functions occurring in orthogonal space. And that's, in a large part, what we're doing when we're using symmetry, is it's helping us spot orthogonality. When will I have essentially a 0 overlap or net interaction in between two different functions, no matter their form, which can be hugely advantageous. So again, what we showed is that we have no overlap in between the px and the py orbitals on SO2. So it's always good to confirm what we suspect should happen will actually happen. And indeed, what you can prove is that there will be no overlap in between the px, the py, the px, the pz, and the pz and the py, because they form an orthogonal set. Now, here becomes the much more interesting question, is how do these p orbitals interact with the pz orbitals on the oxygen atoms? Well, let's go ahead and evaluate this interaction. So we're going to start by looking at how the py orbital interacts with our pz orbitals on the oxygen atoms. Specifically, we're going to be looking at the irreducible representation that we ended up generating earlier uh, when we first introduced irreducible representations of P1. So this was towards the beginning of symmetry. And let's go ahead and look at the overlap in between these two. So if I'm looking at the overlap matrix, which again is going to be crucial when I'm trying to solve when I'm trying to implement molecular orbital theory, what we end up finding is that Py again belongs to B2 symmetry, and it turns out that B1 belongs, or that P1 belongs to B1 symmetry, which I apologize. This should be X and RY here. But if I then try and take the integral of this, the easiest way is going to first be finding the product of B2 and B1. So again, we can multiply our matrix elements, and we're going to again find 1, 1, -1, -1. So our end resulting species belongs to the A2 point group. Congratulations. We got the same result as last time. So the overlap in between these two wave functions will be 0, which again should hopefully make sense, because this was a developing principle that we had when we were building up MOs, because Py belongs in the sigma bonding network. It's bonding along the plane of the molecule. So this Py orbital may end up interacting with the Py orbitals on atoms B and A, but it won't be interacting with the pi bonding network that we find along these Pz orbitals. And because we will have an equal overlap in between this p orbital and the positive and negative nodes, any sort of effective interaction cancels out. So it turns out that we've again supported what we saw earlier this semester, and we shouldn't see any overlap in between the Py orbital on the sulfur and the P1 orbitals located on the oxygen atoms. All right, let's go ahead and focus a little bit more on the pi system. So by doing this, we're going to be focusing on the px orbital on the sulfur, and the, px orbitals on the oxygens. So again, we're going to be looking at the interactions of px and p1. And it turns out that both of these belong to the B1 irreducible representation. So now here's a really good sign. As I told you before, it turns out that if I have two identical irreducible representations and I take their product, watch what happens. So we have 1 times 1 gives us 1. We have 2 negative ones, so we get 1. We have 2 positive ones, so we get 1. We have 2 negative ones, so we get 1. And this will always happen. If you have 2 identical irreducible representations, your product will always be the completely symmetric irreducible representation. Now, it's worth noting that when I take the integral of this value, what it essentially tells me isn't the fact that I know what the overlap matrix is. All it tells me is that the value isn't 0. Doesn't mean that it can't be very near 0, which is indeed what we found when we were solving for the overlap matrices of these systems before. But it means that there is indeed some interaction between these orbitals, which is a very important phenomena to be able to observe. So again, it won't, using symmetry won't always tell me what the values of all the integrals that I need to solve are, but it will help me identify which integrals go to 0 and which interactions I just don't need to worry about. And so what we can do is kind of pull this back out, and let's take a look at the symmetry, at the irreducible representations of all 5 of our relevant orbitals, our 3 sulfur atoms, or 3 sulfur orbitals, and the 2 p orbitals on the oxygen atoms, both P1 and P2. So what we can do is find out what point group everybody belongs to. And using our character tables, we find that Px belongs to the B1, Py belongs to B2, Pz belongs to A1. So again, none of these 3 orbitals will end up interacting. But What you can do is by, again, applying our symmetry operators to our to our p orbitals centered on the oxygen atoms, we'll find that P1 belongs to the B1 point group. It will be anti-symmetric upon rotation and reflection across the XZ axis, but it'll be anti-symmetric upon reflection across the YZ axis. Similarly, our B2 orbital is, or our P2 orbital is going to belong to A2 symmetry, as it's going to be symmetric upon identity and rotation and anti-symmetric upon application of both of our mirror planes. But what this ends up meaning is is that these two sets of orbitals will also be orthogonal. There will be no overlap in between these two orbital series. And it also turns out that A2 will have no interaction with the sulfur atom. But my P1 and my PX orbital will indeed share a symmetry. And again, this is because they can form a pi bond. So just by looking at the symmetry of all of the orbitals, I can identify potential pi bond formation in between the PX and the P1 orbitals. All of my other actions will be symmetry forbidden. And you can also scale this idea up a little bit more. If I was going to construct a set of irreducible representations for the orbitals, for the Py and the Pz orbitals on the oxygen atoms, we'll find that there should be some interaction in between the oxygen Pz orbitals and the Pz orbital on the sulfur atom, and a similar interaction between the Py orbitals, where some interactions will be symmetry forbidden and some will be symmetry allowed. And this general approach to solve can be used to build up full systems of molecular orbitals and identify molecular orbital interactions. And we can apply the same idea to other molecules, including NH3, which belongs to the C3b point group. So we should be able to, using your character table, rapidly identify the irreducible representations of the 4 valence orbitals on the nitrogen atom. The s orbital, as always, should belong to the completely symmetric irreducible representation, because that's an s orbital. Turns out that the Pz orbital will belong to the A2 irreducible representation, while the Px and the Py combine together to make a set of the two-dimensional representation of E. So again, if I have a two-dimensional representation, it means that these orbitals will move together. And this is actually very important when I start comparing it to the hydrogen 1s orbitals. So it turns out that we can start by applying our symmetry operations to our 3 hydrogen orbitals independently. But it turns out when you do that, you can reduce that 3x3 matrix representation to 2 sets of irreducible representations. One being the one-dimensional, completely symmetric representation, which would demonstrate a molecular orbital that is composed of all 3 hydrogen 1s orbitals in phase with a 1/3 contribution from each. Then for the other two orbitals, they combine together to form the 2-dimensional irreducible representation. The first orbital will have a 2/3 contribution, sorry, a 1/2 contribution. We'll have a majority contribution from one 1s hydrogen, and then a minority contribution from the 2 other hydrogen 1s orbitals. And then the final one will have a anti-symmetric combination of those remaining 2 hydrogen 1s orbitals. When you add these all together, you'll end up finding coefficients that will end up adding together to 1. as again demonstrated with our molecular orbital theory. But symmetry can help us identify the general shape. But what I want to focus in on here is that again, because I have a two-dimensional matrix, because these two hydrogen 1s orbitals will form a two-dimensional irreducible representation, they're also going to come together in a paired set. So when these two interact, they will always interact as a pair. This means that they will form bonds as a pair and they will form lone pairs as a pair. They'll always move together and they'll form a degenerate level. And again, this also matches up with what we saw previously, because orbitals can only ever interact with other orbitals who are of the same irreducible representation. So in this case, what we can do is identify we have two sets that belong to the E irreducible representation, or that's two-dimensional irreducible representation. So that means that these sets of orbitals can overlap to form bonds. And if you have a good eye for this, what you can note is that these two orbitals can end up interacting. A symmetric combination will end up forming an overlap in between this hydrogen 1s orbital and this nitrogen 2p orbital, or 2s and 2p orbital, and a more mild overlap in between these hydrogen 2s or 1s orbitals and this nitrogen 2p orbital. And then that leaves a interaction or bond formation in between this nitrogen 2p orbital and this hydrogen 1s orbital. And it turns out that when you combine these, they will have identical overlaps, even if it might not look so from first glance. And this will end up generating two sets of both bonding and anti-bonding orbitals that will be identical in energy. But we can also notice that we aren't quite done yet, because we also have two sets of orbitals that belong to the completely symmetric representation. So these two A1 orbitals will also end up overlapping. The symmetric in-phase overlap will give us our bonding orbital, and the anti-symmetric overlap will give us our anti-bonding orbital. That leaves this last nitrogen 2pz orbital belonging to the A2 subgroup as non-bonding. It will not interact with any of the hydrogen orbitals, meaning that this is indeed our lone pair. So just by looking at the symmetry, with a little bit of practice, it is possible to help use this to help to show how our orbitals can form together to make full molecular orbital pictures, and to get a rough idea of what those energies should look like, because when solving my MO matrix, I can quickly identify any interactions besides the ones I just overlapped will give a overlap integral of 0. However, what we haven't shown is that the resonance integral should also end up being 0 for any overlaps between wave functions of different symmetries. For that, we're going to need to take a little bit of time and look at the irreducible representations of operators. So we'll do that next time and wrap up our little side jaunt into symmetry. Until then, take care and stay healthy.